All right, folks, welcome back. I think this should be the last video of the series here. You see in the last video, video 5, we achieved quite remarkable convergence. We got our successive difference between density matrix values down almost to 0. Things have converged. So that leads us then to step 12 of the 12-step method, which is really just calculate whatever it is you would like to. I don't have a real strong chemistry background, so I don't understand necessarily everything I'm calculating here, but if I found a formula for it somewhere, I tried to go ahead and use it. For one thing, it gives good confirmation that we have good converged values here. So let's just go through and take a look at these. I'll try and hopefully this will all finish up in 15 minutes or so. So, yep, step 12, post-convergent calculations. We can calculate the orbital energies here from the eigenvalues that we calculated before. So there's the orbital energies for 1 and 2. We can calculate the total nuclear energy by taking the electronic energy that we've calculated and just add to that the repulsion between the two nuclei, which is fixed for a fixed R value. We put in an R value of 1.4 or something like that, fixed for this this run. So this is just a number. We can add it on. So the nuclear value is a 1.366, and if we add that on to our electronic value, then we'll get a total value. So once again, here's the electronic value using equation 3184. Here's calculating the electronic value again, just using a kind of a modification of the same equations. It's good to see these same numbers show up here. Negative 4.22753. We should see those again and again. Then we can calculate the total energy by adding on the nuclear repulsion term, giving us a negative 2.86 for the whole deal here. If a person were running this program because they wanted to find the bond length, then you would put in different values of R up at the beginning of the program, and then you calculate this E total, and then where you found E total to be a minimum value, you would take that to be your optimum bond length. So this negative 2.86 should be about as low as you can get for placing the helium nucleus and the hydrogen nucleus. Okay, here's population analysis stuff. See page 177. I don't have a real deep understanding of what this means, but the formulas are easy to use. So there's something called a Mulliken population analysis and a Loudon population analysis. So the values should agree with those given in the textbook. They do. They give an interpretation of them, what they mean in there. I was just interested in replicating the values. Somewhat more generalized is the Loudon population analysis. Notice that this is actually raising a matrix to the 1/2 power. This is not the S1/2 matrix that we had before for normalizing. This is actually raising a matrix to a power, so I have to use the matrix power subroutine in Mathematica to get the right value. So I'm saying raise matrix S to the 1/2 power, or the square root. That's what's called for here. So I do that, and I get using equation 3277 in Zabel-Osland, and I get the same value they do. Interesting mathematical thing is to show that these two are actually equivalent. It's not real obvious to me that these two equations yield the same thing, but they should, and they do. So it's good to see that here. Something on a to-do list for me is to see somehow if I can show formally that these two expressions are equal to each other. Maybe it's pretty easy. I haven't tried, but we can see here they do give the same value. Just calculating some pieces here for comparison purposes. So yeah, there you go. Comparing the pieces that go into these two different formulas for the loaded population analysis. Another thing you can do is when you have the Fock matrix is you can just set it up and solve it as a secular determinant. So I did that, set up the secular determinant in the usual sort of way, but using the converged Fock matrix that I got, and then solve that. So I used Mathematica's built-in solve routine to solve the determinant, the secular determinant, solve it for 0. And it gives me our values here, our eta 1, eta 2 values. So call it here eta 1, eta 2. There they are, negative 1.59.06. So just another way of getting those. Calculating a Hamiltonian matrix here using equation 3.241. So I did that, and values seem to be okay. Switching things over here into a psi basis rather than the basis of the two orbitals that make it up. Using equation 3.242, I put together a set of psi values. And this is kind of nice. From these I can put together exchange and integral matrix values. So page 164, bottom of the page, I get a J matrix. 164, bottom of the page, I get a K matrix. J is the Coulomb integral matrix. K is the exchange integral matrix. So kind of fun to do that. It's going to let me in just a little bit calculate the electronic energy using the standard what do you call it, the Slater-Condon matrix evaluation rule. Can use it directly and calculate the energy. Calculate a Fock matrix here in the new psi basis, and calculate electronic energy from those numbers. Yep, it's good to see you get the same thing that we've been looking at up there. Is it? Yes, 22753. So yeah, that's good. 22753. This is one of my favorites here, 3181. This is just the standard matrix evaluation rule, but since we've calculated J and K matrices, I can use it directly to calculate the energy. So once again, get the same value. But to me, it was kind of fun getting it from this formula, because I think of this, or I thought of this as kind of a formal equation that you would never really use in a computation, but you can at this point if you want to. Okay, I can calculate orbital energies from the Coulombic matrix and the exchange matrix, and I get my 1.54906 numbers again. And then just kind of try different things here. Yeah, I concluded there are so many ways to get the diagonalized Fock matrix. Yeah, and then just take our solution that we have and plug it back into the Rutan equations and just verify that we solve them. So this is the non-eigenvalue looking equation because of the non-orthogonal S matrix, but we should have solved it. We did solve it. So calculate the left-hand side of the equation, calculate the right-hand side of the equation, and they should agree. The left-hand side equals the right-hand side. So just checking, plugging our answers, you might say, back into the equations and verifying that we solved the equations. So yep, Fock matrix times coefficient matrix does equal the overlap matrix times the coefficient matrix times the orbital energy matrix. So just fun to see it, fun to see those equations really work. And then in the prime basis, the F prime basis, we orthogonalized it and got rid of the overlap matrix, and that's the one we really solved iteratively as an eigenvalue eigenvector problem. So plug back into that, should see that we solved that also. Yep, the left hand side equals the right hand side. And then finally, just winding up here, just plugging into a few identities that you see in the textbook that we should be automatically satisfying here. C dagger times overlap matrix times C should give me the identity matrix. So yes, indeed, I am, according to equation 3.10. 3.12 says density matrix times overlap matrix times density matrix should give me 2 times the density matrix. That's also something I'd kind of like to prove sometime, but I haven't proved it at this point. I'm just checking to see if I did. So there's P times S times P, and there's 2 times P, and yes, they do agree. PSP does equal 2P, so heartening to see that, encouraging to see that. According to 3.166, U dagger SU, where S is the overlap matrix, should equal the little s matrix, the values we saw up there just at the beginning of this lesson. So check it. Yep, they do. The orthogonal S matrix, the little s matrix. Yeah, it's in agreement. And then finally, 3.165 is X dagger times overlap matrix times X. X was our change of basis matrix we were using. Should give us the identity matrix, and it does. So we feel really good. So that's about all I could think of to calculate here from the converged results. If a person with a good heart for chemistry can probably calculate a lot more things, but these things at least gave good verification that we had internally consistent values. So with that, thank you for watching. I'll try and come back maybe a little later with a video. We'll modify this program to use a 6G basis rather than a 3G basis for building the Slater orbitals. So hopefully see you later for that, but we are done. This completes the the helium hydride self-consistent field calculation. So thank you for watching. Goodbye.